Hello class, welcome back. Today I'm going to be going over chapter 9, and chapter 9 talks about magnetism and electromagnetic induction. Alright, so let's get right into it. So, again, basically I'm just going to be following the slides. Some things I'm going to skip over because I'm sure you can just read for yourself. Other things I'm going to try to more so elaborate on that may be hard to understand. So basically in this lecture, I'm going to be going over magnetic poles, magnetic fields, magnetic domains, electric currents and magnetic fields, magnetic forces on moving charges, electromagnetic induction, generators, alternating currents, power production, transformer, and field induction. Cool. So, the first thing I want to get into and try to describe to you is magnetic poles, fields, and forces. So first, let's get into magnetic poles, fields, and what else? Forces. Boom. So first of all, a magnetic pole, which I'm sure you can probably guess, is basically the north or the south pole of a magnet. So let's say this is a magnet here, right? And this is the north pole and this is the south pole. And of course, just from kind of already probably personal experience that you've had with magnets, if I bring another magnet over here, and this side is also the North Pole, then these two magnets are going to basically they're going to push each other away, right? So basically, magnets kind of follow a similar rule that charges follow, right? That being, like poles repel and opposite poles attract, just like opposite charges attract and, like charges repel, right? So, basically this is what the north and the south pole of a magnet, right? And if I were to break this magnet in half, if I were to break it in half like this, boom, if I were to break it in half, this part of the magnet would not just be the North Pole. Now this magnet's going to become North Pole, and this part's going to become the South Pole, and this is going to be the South, and then this is going to become the North. So if I break a magnet, now I have two magnets. I can't actually break the pole in half. So similarly, if I were to break it again, now it looks something like this. Well, now instead of having like a north-south, north-south, I actually now just have four separate magnets, where now I have a North Pole, a South Pole, South Pole, a North Pole, North Pole, South Pole, and let's see what else, South and North, boom. So basically, the more that you break a magnet apart, you basically just get more and more little magnets. So now let me draw how the field would look for a magnetic pole. So let me use a different color. So let's say again, we got our bar magnet. This is what this calls a bar magnet. So the magnetic field is going to come out of the North Pole, basically, out of the North Pole, all right, and then kind of circle back around and go into the South Pole. So the direction of the magnetic field is always going to point away from the north and towards the south. So it's going to point away from the north, and towards the South Pole. Boom, and then see, you got some going out this way. Pointing outwards, outwards, outwards. These point inwards, inwards, inwards. Boom. So this would be how the magnetic field lines look for this magnet here. And these field lines follow similar rules as the electric field lines, Like, the closer these field lines are to each other, the stronger the magnetic field is in that region. Or the more spread out apart the magnetic field lines are. So like these two are really spread out. So the magnetic field in this region is less than in this region. So the closer the magnetic field lines are to each other, the stronger the magnetic field is in that region. So obviously it's strong around this region, strong around this region. You know, kind of strong there and pretty weak as you get further out, right? So that's kind of all you need to know for magnetic field lines. Just know that they point away from the North Pole and towards the South Pole. And the further you get away, the weaker the magnetic field is. And the more spread out the magnetic field lines are, then the weaker the field is. All right. So let me draw the field lines for one more magnet. I'm gonna also draw the field lines for a U magnet. A U magnet basically is a magnet that's shaped like a horseshoe. Boom, like that, cut in half. Over here is the north, over here is the south. So again, basically it's gonna point away from the north, right, and towards the south. So straight like that. And we have another one like that. Then maybe like another one way up here. Say one up in there. And then some pointing outwards here, pointing inwards there. Something like that. So for a U magnet, obviously it's going to be strongest right up in this region. And then out here, the magnetic field's still going to be there, but not as strong as within this region. So that's how you kind of do magnetic field lines for, for the North and South poles. And now, let's see, magnetic forces. Well, we know two magnets will exert a force on each other, right? So I've kind of already talked about forces a little bit. So we know basically that opposite poles attract. So South Pole, North Pole, South Pole, these opposite poles are going to attract. So once these two magnets get close to each other, they're going to be pulled to each other by some magnetic force and, basically come together. And same vice versa, if this were north, not the same, but, the opposite would happen. So if the two North Poles get close to each other, they're going to basically push away from each other. So you could basically put these two North Poles together, but you would have to hold them there by some external force. If you were to let them go, they would push each other outwards. All right. So now that we kind of have an idea of, magnetic poles, fields, and forces, what exactly is causing this magnetic field? Well, the simple answer is going to be basically the atoms that are inside of the object that we're talking about. So we know all mass is made up of matter, and that matter is made up of atoms, and then those atoms are made up of protons, electrons, and neutrons, right? Well, it's the electron. So it's basically two things that's causing the magnetic field. Let me draw an atom here. So these are our neutrons there. Let's see, it's our electrons out here, and our protons up in there. And then this electron spins around, has a negative charge. So this electron spinning around here is actually what causes the magnetic field. It's one reason. And then this electron is also spinning. So this electron is also spinning on its own. So kind of, if you were to imagine the Earth revolving around the sun, as well as the Earth spinning, right? So the fact that the electron goes around, then spins around this atom, causes a magnetic field, as well as the fact that this electron is spinning also causes the magnetic field. So something like that, north, south pole. And another north and south pole. Where this one here is basically caused by the electron going around that center, and then this one here is from the electron spinning on its own. So that basically is what causes the magnetic fields inside of objects. So what makes an object, a magnet, and another object a non-magnet? Right, because we know all objects have matter, hence they all have atoms, but not all objects are magnetic, right? There's only certain, items that are magnetic. Then there are only certain things that will be attracted by magnetic items. So let's say I have some block here. You know, this block is made up of atoms, right? So actually, let's say I have two blocks. This is a block, and let's say this is an atom, or this is a magnet. Boom. So this is just some block, right? It's not a magnet, it's just some block. So it's basically neutral, right? But this magnet, basically what makes it a magnet is that all the electrons inside of it are lined up. So all the electrons, you can imagine all the electrons inside of this are kind of pointing in this direction. So they're not really moving, but they're pointing in this direction. So the electrons pointing in this direction makes this item a magnet, and they're stuck that way. Now, this magnet, and let's say this is iron. So iron has a whole bunch of atoms in it as well. So the atoms inside this iron object will then be magnetized by this magnet here. So basically, if I bring this magnet next to this piece of iron is going to be attracted to the magnet. Then so this magnet is going to magnetize, they say magnetize the atoms inside of this piece of iron. So beforehand, the electrons were all random. And then bring this magnet along, it's going to basically align all the electrons in this piece of iron, and then they're going to be attracted to each other. So in short, that's basically what makes objects magnets. So it's the atoms inside of that object that makes it a magnet. And that's basically the simple answer for it. All right. So now that we've kind of talked about magnetic fields, forces, magnetic poles, and what causes magnets, now let's see. Let's go over. Let's go over what else can create a magnetic field. So we know there's objects called magnets that obviously have some magnetic field around it, right? Well, another way a magnetic field can be produced is, another way a magnetic field is produced, magnetic field is produced by moving charges. Boom. So this here is kind of a big deal because we once thought, magnetic fields or magnetism was a whole separate thing from electricity. But once we found out that charges can produce magnetic fields, well, now there must be some link between electricity and magnetism. So a moving charge can produce a magnetic field. So what is a moving charge? Well, a moving charge is basically a current, right? So let's say I have a wire like this, and this wire has a current going in that direction. Remember, we use I for current. So inside of this wire, there are moving charges. Okay, so if there are moving charges in this wire, then this wire must be producing a magnetic field. And the magnetic field that this wire produces is basically a magnetic field that kind of revolves around the wire in a circular fashion, kind of like this, going in this direction. Boom. So this wire, since it has some current or moving charge, is going to produce a magnetic field that basically rotates around it circularly, and it's going to basically emanate outwards. So it'll be out here as well, going in that same direction. But of course, the further away we get from the wire, the less and less the magnetic field is going to be. If we're really, really close to the wire, the magnetic field is going to be a lot stronger. So how do we know that the magnetic field is going in this circular fashion? Well, we know that from something called the right-hand rule, and I'm going to get into that right after explaining this next part. So I'm going to come back to this. Come back to that. So let me go back to the magnetic force now. So as I just said, we know that basically magnetic fields are produced by moving charges. So now let's say we have a charged object, say that wire, right? A moving charge, let's say this wire. And some current that way. If I were to put this current inside of another magnetic field, so we know this current produces its own magnetic field, but if I were to put this current inside of another magnetic field, so let's say I put a horseshoe magnet around it. Let me do red. So this is the horseshoe magnet. Boom, right? Let's say over here is the North Pole. Over here is the South Pole. So now we have basically this wire. This wire carries some current, and it's producing its own magnetic field. And we put it inside of basically this other external magnetic field made by this bar magnet. Well, now there's going to be a magnetic force on this wire pushing it in a certain direction. It's actually going to push it upwards. So the magnetic field from the bar magnet is going to go in this way. Goes from the north to the south, right? Boom. So the magnetic field goes that way, kind of goes across the wire. And that's going to cause the wire to be pushed upwards by the magnetic force. So basically what I'm saying is, if we put this wire inside of this external magnetic field made by the bar magnet, it's going to be pushed upwards to where it's basically upwards like this through this dotted line path. and it's going to be pushed upwards due to the magnetic force. And it's pushed upwards because of the right-hand rule that we use. So the right-hand rule basically tells us which direction the magnetic force is going to be. So I'm going to write that down here. RHR for right-hand rule tells us the direction of the magnetic force. Boom. So now let me try to explain how we do this right-hand rule. So if we take our right hand, our thumb is going to represent the charge in motion. Let me try to draw it out first. I'm going to use V. For this is basically the velocity of the charge. So think of this as kind of the direction of the current. I'm going to use V for that. And then let's say the magnetic field, I'm going to use blue for that. And we use the letter B for magnetic field. So B equals magnetic field. So if the current's going this way and the magnetic field is going basically perpendicular with the current, then the force is going to be upwards. Boom. That's going to be the force. So how we do that with our hand is the thumb, sorry, it's paint on my hand. So our thumb is going to be the direction of the moving charge. So it can be the current or it can just be the velocity, depending on the scenario. So here, let's say it's the current. So my thumb represents the current. My fingers here, are going to represent the magnetic field. And so whatever direction my palm is going to be the direction of the force. So basically, my thumb is to the right because the velocity is to the right. Fingers are upwards, perpendicular with the velocity because that's the direction of the magnetic field. And my palm basically points upwards, so the force is going to be upwards as shown here. So now let me go back to that current going through the horseshoe again. And let me draw. Let me do it a different way. So now let's say we have a current. Let's say it's going this way. And we have our horseshoe magnet. Boom. Boom. And this is the North Pole. Over here is the South Pole. So we know the magnetic field is going to point away from the north towards the south, right? So the magnetic field points that way. So now, which direction is the magnetic force going to be? Well, using our right-hand rule, the direction of the current is going to be our thumb. So our thumb's going to point basically towards me, kind of this way. So here we'd have to kind of put our hand downwards. So my thumb here represents the current. My fingers represent the magnetic field going that way. And so my palm, the inside of your palm is the direction of the force. So the inside of my palm points downwards. So the force here is going to be downwards. So the force is going to be downwards. And that basically means this wire is going to be pushed downwards due to the magnetic force. So let me do a few more examples because the right-hand rule is kind of tricky. It takes some practice getting used to putting your hand in these different ways. But here, let me explain one more time. So my thumb is going to be the direction of the current, right? So thumb pointing in that direction. Fingers here are the magnetic field, they're pointing in that direction. My palm is facing downwards, so the magnetic force is going to be downwards. So let's do a few more examples of the right hand rule to give you more of a feel for it. So let me draw some magnetic fields here. This here is a magnetic field. And this here is another magnetic field. So these are two magnetic fields, and this magnetic field is going into my board here. It goes into the board, and this one comes out of the board. So basically, what you want to remember for these two is kind of think of a bow and arrow. So say you have a bow and arrow where this is the tip of the arrow and over here is the tail of the arrow. And the tail of the arrow looks kind of like that or something. It's got like some flares back there. If you imagine this arrow coming right at you, so like you're standing and this arrow is coming straight at you, what you're gonna see basically is the front of the arrow, right? So you would see basically these dots. So if you're looking down at this board and you see these dots basically represent the arrow coming straight at you. Or in other words, the magnetic field is coming out of the board. So this represents the magnetic field, B for magnetic field, right? It's coming outwards. And similarly, if you were to see this arrow, going away from you, you would see the tail, right? And so you can imagine here, you're looking down at the board. This would be the tail of the arrow. So the arrow is going into the board, or the magnetic field is going into the board here. And so that's why we use these dots and X's to represent magnetic fields. Now, otherwise, we would just use left or right. So something like either a magnetic field going that way, which you can easily just represent by drawing an arrow, right? Or you can do it drawing it up, left, so left, right, up, or down, right? Then you can also go in and out. And so this would be into the board, this would be out of the board. And of course, this would be to the left, to the right, up, or down. All right, so now we have these two magnetic fields, right? So now let's say I have a charged object and it's gonna go inside of this magnetic field. Say I have a positive charge. Positive charge here. This positive charge has some velocity v. So once it goes inside of this magnetic field, it's going to experience a magnetic force, because moving charges experience forces, magnetic forces, when they're inside of an external magnetic field. So now the question is, what is going to be the direction of the magnetic force on this positive charge? Okay, so once this charge goes inside of this magnetic field, it's going to feel some force in some direction. So let's do the right-hand rule here. So again, taking our right hand, my thumb is going to be the direction of the velocity. So our thumb is going to point towards the right. And here, notice that the magnetic field is going to point into the board. So my fingers are going to be pointing downwards. This is going to be kind of difficult to do, but imagine my fingers kind of pointing all the way down, like so. Can't really bend my hand that way, but you can kind of imagine my fingers pointing all the way down, right? And my thumb still pointing to the right. Yeah, and so then my palm would be the force, right? So let me write that out. So the force is going to be the palm. Goes the palm. The velocity for V is your thumb. And the magnetic field, B, is your fingers. Boom. So have your thumb, go for your thumb, fingers, and then palm. So thumb to the right, fingers downwards, palm points kind of upwards. And so the force here is going to be upwards. Boom. So once this charge gets inside of this magnetic field, it's going to experience a force upwards, and that's going to cause it to basically curve. It's going to cause it to curve and go in some direction like this. So once this charged object gets inside of this magnetic field going into the board, it's going to experience a force upwards, causing it to basically curve, turn around, and do a circular path here. And basically what's happening is once it gets here, it experiences force upwards, and then once it gets to this point here, the force pushes inwards, then kind of causes it to turn around. So let me do that again for this one. So again, we've got some positive charge going this way into this magnetic field coming out of the board. So then the question would be, what direction is the force on that charge? Well, again, our thumb is pointing to the right. Our fingers for the magnetic field is coming out of the board, so it's going to be upwards. This is a little bit easier. And so see, my palm is basically pointing towards me. And so the force here is going to be downwards. So the force here is going to be downwards. So here, the charge is going to circle around this way. Boom. Just like that. So again, this takes a little bit of practice. The right-hand rule is not intuitive in any kind of way. It's not something that you would feel is natural, right? You kind of just have to practice this, get your hand in all kinds of different ways and then get used to it that way. So that's the right-hand rule for a positive charge. Now, this is always true for a positive charge, but for a negative charge, if we were to have a negative charge, the right-hand rule is always flip the opposite way. So I'm going to use green here for a negative charge. Let's do for this magnetic field coming out. So that was our positive charge, right? Let's say I have a green for a negative charge, and it's going into this magnetic field. Well, of course, it has its velocity going towards the right? And the magnetic field is still coming upwards. But instead of the force being downwards like before, since this is a negative charge, the force is going to be opposite, pushing it upwards. So this negative charge is going to feel a force upwards. And so a negative charge is going to circle around this way. So important to kind of make this difference here. So a positive charge always follows the right-hand rule, basically. But for a negative charge, it follows the opposite of the right-hand rule. So for a negative charge, if the right-hand rule says downwards, it's going to be the opposite. It's going to be upwards. Similarly, if I were to have a negative charge over here going in that way, instead of the force being upwards, the force is going to be downwards. And it's going to go in that direction. Boom. So that's going to take a little practice. Just let that sit, think on it, take it slow. And so now let's see. So now I'm going to go over, boom, 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 boom. So now that we get the idea of the magnetic force, so let me actually give the equation for that. Just real quick here. So this may be how you see it in the book. This is something called a cross product. I don't think you have to worry too much about what this cross product is or what it means, but just know that basically the magnetic force, so this is the magnetic force, and put a little M there. This is basically the force on a charge. So this is the force on a charge with some velocity moving in some external magnetic field. So if you have some charge with some velocity moving in an external magnetic field, it's going to experience some force, some magnetic force. And the direction of that force is given by the right-hand rule. Okay. So now we know that basically magnetic fields can be produced by moving charges, right? So now the question is, if a magnetic field can be made by a moving charge, so basically a current can produce a magnetic field. So a current can produce a magnetic field, right? Because a current is just a moving charge, and moving charges make magnetic fields. So if a current can make a magnetic field, now the question is, well, can a magnetic field produce a current? Interesting, right? Because we know a current basically carries charge, and we do all kind of things with currents, whether it be a power supply, charge our phones, laptops, power our houses, power, basically everything in our technological age. So now the question is, well, current can produce a magnetic field. That's cool, but it would be even cooler if a magnetic field could produce a current, right? Because we can do all kind of stuff with currents. With magnetic fields, they just kind of, attract and repel. So, question is, can we go back this way? Can a magnetic field produce a current? Well, the short answer is basically yes. A magnetic field can produce a current, and this was discovered by Michael Faraday, and it's called electromagnetic induction. It's a mouthful. Electromagnetic induction. So electromagnetic induction basically just means either a current or a magnetic field being induced. Just kind of think of it that way. So how this was discovered is, let's say we have a coil. Boom. So this is some coil, basically a wire, and it's just wrapped around here, and it's connected to some battery here. And this battery basically is gonna cause a current to go through, right? It's gonna cause a current to go through this wire once we connect that battery. So we got this circuit here. So we know if we connect this circuit to a battery, then a current would flow through it. Now let's say we take the battery away. There's no battery now. So now basically all we have here is just a wire that's wrapped around here. That's all it is, it's just a wire. So this wire is, no, it's not charged, it's not magnetic in any kind of way. No, it's basically neutral, even though it does have electrons in it, but the electrons aren't doing anything because there's no power supply, so there's no current. So basically it's just a wire sitting there on the ground. It's not doing nothing at all. So now, if we take a magnet, and so Michael Faraday tried all kind of things. You put this magnet, put it inside of there, he brought it near it, and nothing happened until he realized if he was to, move this magnet through this loop here, then that would cause a current to go through this wire. So if I take a magnet and I basically place it inside, not just place it, but actually move it inside. So say this is the magnet, say I move it inside of this loop here. If I move it through the loop, it's actually gonna cause a current to go through the loop. So basically a current or electricity is produced just by me moving a magnet inside of, this wire here. And then even the faster I move it, the more current that's made for that short time. So if I move it really, really fast, like up and down, then that's gonna produce, a nice current going through here. Another way we can induce an even more amount of current is, let's say we put more loops through this wire. So we wrap this wire around a lot more. So if we add more loops, then we put the magnet through it, it's going to produce even more of a current. So there's two ways we can increase the current here. We can increase the movement of the magnet, or the change in the magnetic field. It's basically what's happening here, because the magnetic field is changing inside of this loop. So the faster we change the magnetic field, the more the current's going to be. Or we can add more loops, and then the more loops there are and then we do, put our magnet through it, then an even greater amount of current will be produced. And so that's basically called Faraday's law. So let me just put that into words. So now we have something called Faraday's law. And this is basically the law for inducing currents. And so it says an induced voltage where basically this voltage is kind of like the current, right? Because voltage equals I times R. So this voltage basically is making that current. So this is Ohm's law. And so it says induced voltage in a coil is basically proportional or related to, I'm going to use this little squiggly line for related. I'll just write it out, it's related to. It's related to the number of loops and the number of loops actually times the number of loops times the rate. Well, the rate is basically how fast times the rate of change of the magnetic field. Boom. So the induced voltage or the induced current in a coil is related to the number of loops, so however many loops times the rate of change of the magnetic field, where this is basically just how fast the magnet is going through those loops. So basically the current here is related to, I'm going to use the squiggly line, related to the rate, and so the rate times the loops. Don't really need to worry about the equation for Faraday's law, just kind of understand how it's related to the rate in the loops. So if we want to increase the current, we can either increase the rate, so you increase the rate, or increase how fast you change the magnetic field. That increases the current. Or you can increase the rate, or you can just increase the loops. So you increase the loops, then that increases the current, or you can increase both of them, right? Increase both of them, then that definitely is going to increase the current. Same thing happens if you decrease the loops, then that would decrease the current, right? Well, if you were to decrease the rate, then of course the current would also decrease. So that's basically all you need to know about Faraday's law right there in a nutshell. Is basically changing a magnetic field near a wire induces a current in that wire. All right. So let's see, looking through the slides. Okay. So there's one slide on here that I kind of want to explain a little bit. It's going to be slide number 33 if you're looking at the PowerPoints, but if you're not, I'm just going to describe it here. Basically, we have a picture of a whole bunch of loops here. It's a lot of loops, probably 1,000 or so loops or something. Boom, they're connected over here. And there's a picture of a person here. Trying to push a magnet into the loops. So this person is trying to push this magnet downwards into the loops. Well, we know since this is a magnet and it's going through basically this closed loop, it's going to induce a current, right? Well, the slide says it's more difficult to push the magnet into a coil with many loops because the magnetic field of each current loop resists the motion of the magnet. So what are they saying there? So let's say this is our North Pole, this is our South Pole. When we basically put or we try to push this magnet down with some velocity into this loop, it's going to induce a current into this wire. So let me try to put it in order. So first, we have magnet pushed in. All right. So first, when this magnet gets pushed in with some velocity, then number two, the second thing that's going to happen is a current is induced. Put it in red. A current is induced. Right? That's basically Faraday's law. So you push this magnet in with some velocity, a current's going to be induced through this wire. So let me draw that on here. So now there's a current induced in a wire. Well, what do we know about basically wires that carry a current? So basically 3 is that wires that carry a current they basically produce a magnetic field as well, right? So now we know currents produce their own magnetic field. Boom. So now we have an induced current. This induced current also produces an induced magnetic field that's made by the current. So now we have a magnetic field inside of this loop here going upwards in this direction. And so now this magnetic field, this induced magnetic field, I'll call it induced. It's induced. This induced magnetic field is basically pushing upwards against this other magnet, hence making it hard for you to push this magnet downwards. So again, let me try to reiterate this. So we have a magnet. This magnet is being pushed inside of this loop here. Since this magnet is going in with some velocity, a current's going to be induced. So now, as this magnet is being pushed inside, there's a current being produced inside of this coil. Now this current also produces its own magnetic field. So now we have an induced magnetic field. And it's basically going upwards inside of this coil here. So now this induced magnetic field is pushing against this magnetic field, making it harder for you to, push that magnet in there. So that basically takes a couple of steps of logic to kind of see that happening. But if you were to imagine, let me think, there's an experiment, which is a pretty cool one. Very similar to that. Let's say we have this here. Boom. So let's say this is basically some copper cylinder. This is a copper cylinder. So we know copper is a conductor, meaning that it can carry some charge. So this is just some copper cylinder. If we were to drop kind of a circular magnet down this tube inside of the copper, this copper is solid, and we're going to drop it down inside of it. As this magnet falls through this tube, it's not just going to fall, regularly at free fall. Once it falls inside of this tube, there's going to be a magnetic field induced inside of this copper wire. It's going to push it back upwards. And so as this magnet falls downwards, it's going to fall really slow. So this magnet's going to fall slow. It's going to fall slow because the induced magnetic field is pushing against it. And I'll probably post like a YouTube video of that just because it's kind of cool to see. So now, let's see what's next. Now let's get into transformers. So what is a transformer? You probably might have heard about a transformer, but didn't know exactly what it is. I don't mean like the robots in disguise. A transformer is basically an electrical setup that either boosts or lowers voltage. So a transformer is some type of electrical setup that either boosts or lower voltage. And for the most part, it looks something like this. We have some type of core here, usually made out of iron. So let's say this is iron. And we have this iron is wrapped up over here. And this is connected to the wall, let's say. So we have this iron core is connected to the wall, and then basically this wire loops around this iron. And there's another loop on here. Not as many, different number of loops. And let's connect that to a light bulb. Boom. So basically the whole point of a transformer is to either boost or lower the voltage. Well, this has to be the case sometimes because we know if there's too much current flowing through an object, so too much current flowing through a light bulb, let's say, the light bulb could blow out, right? So we don't want too much current flowing through certain electrical objects, so we use transformers to lower the voltage. So let's say, this is connected to the wall, got some big current going through here. This current is basically going to induce a smaller current in this other coil, a safer current that can pass through this light bulb. So basically, this is what we call like a step down. So this original current that's really, really big was lowered so that it can go through this light bulb. And basically the equation for that is going to be, we have something called the primary voltage. Primary voltage divided by the number of loops. Number of loops for the primary voltage equal to the secondary voltage divided by the number of loops that one has. So we see here if we have some primary voltage, let me try to do an example real quick here. Let's say we have some primary voltage of, I'm gonna call it P for V prime of 1000 volts. And let's say the number of loops is the number of loops. I'm using N for number. So the number of loops for P, the primary, is, let's say 50. And let's say the secondary, I use number for number of loops, and S for secondary is 10. So what would the voltage for the secondary be? Well, using basically this equation here, we can solve for what the secondary voltage is going to be, because we know the primary voltage, we know the number of loops for the primary voltage, and we know the number of loops for the secondary voltage. So let's see, we see then that, let's just put in the numbers here. This is going to be 10. This is going to be 50. And this is going to be 1000. 3. So now we could solve for this secondary voltage by just multiplying 10 over. And see, what's that going to give us? And then dividing by 50. So 1,000 times 10 divided by 50. So the secondary voltage is going to be 200. So notice here, the secondary voltage is way less than what the original voltage was. And we're able to solve that by using, basically the voltage over the number of loops equals the secondary voltage divided by that number of loops through that one. So this would be basically a step down transformer because it was lowered. And we can probably go the other way around to step it up if you were to increase the number of loops. And so that's just like a general idea of how you would use this equation here. All right. So I think you can read the rest of the PowerPoint on your own. This video is already about an hour long now. So yeah, I'm just gonna stop there. You should be kind of good to go with doing the homework. Just kind of look over the chapter a little bit if you're having some trouble with more of like the math side of it. And what else? Yeah, I think that's it. Good luck with your studies. This is week 3 now. I'm glad you all kind of stuck with me throughout this. I hope you're learning something. I hope the class is at least a little bit interesting. I know some of these subjects are harder than others, but, again, just got to take your time with it. This is, hundreds and hundreds of years of information that I'm trying to compact into an hour, and then that you yourself are trying to just understand. So, yeah, just take your time, keep studying. See you next time.